Hey you all, this is video 1.6.5 where I'm trying to help you better understand your trig identities and the rationale for where they came from. Now I debated just assigning this video that is attached in Google Classroom about the Magic Hexagon, but I thought without some context it might be kind of hard to understand, and I thought with context it would make a lot more sense. Now you all need this because you're about to start finding limits of functions that need you to know your trig identity. So I wanted to make sure we reviewed that, or maybe learned it for the first time before I assigned, before you tried that next stuff in Khan Academy. I'm going to start by sharing the objectives for this video. I want to demystify what an identity is. You're actually very familiar with math identities. You've seen them throughout your entire math career, and trig ones are just another version of what you've seen before. So I'm trying to demystify what might seem like a scary idea of a trigonometric identity. And then I want to show and explain how setting up the Magic Hexagon can help us remember and help us find trig identities if we're struggling to find a limit that requires us to know one that maybe we don't know off the top of our head. So I'm going to stop sharing this, and actually no, I want to start with this idea. So at its most fundamental level, all an identity is essentially a need for substitution. It's finding two equivalent expressions. So I'll give like a really basic algebra example. Use my mouse. If I had this equation, a times b equals 12, we could find and guess a bunch of values for a and b, like a could be 2, b could be 6, a could be -3, b could be -4, but we wouldn't know the exact value of a unless I knew more information. But as soon as you tell me, hey, b equals 3, now we know with confidence that a equals 4, and now we can solve this equation if you were asked to solve for a in the first place. That's at its most basic what trig identities are. It's an equation, or in our case, a limit that we really can't find the exact limit for algebraically unless we know an equivalent value for what's already in the function. So that's what we're going to work on right now. I'm going to stop sharing this and share just a little background information about what an identity is. I like this Wikipedia definition. An identity is an equality relating one mathematical expression A to another mathematical expression B, such that A and B, which could contain variables, produce the same value for all values of the variables within a certain range. And I want to show you that you actually do know a lot of identities. Stuff like the additive identity. If I add 0 to something, I have the same value. If I add like the inverse identity, if I had opposite like values with opposite signs, that always equals 0. The associative property is also an identity where I can add and group things together. I can add in different orders. I can subtract as long as I have the opposite. I'm adding the opposite sign. Those are all examples of identities, and I'll let you just look at all of these multiplicative identities right here. But these are things that you are used to. That's all an identity is. It's an equivalent expression. I'll go back to this Wikipedia page to show you a few more that you are definitely familiar with. So like right here, we have the sum of squares. If I multiply, or if I square the quantity a plus b, when I expand that out, I always get a squared plus 2ab plus b squared. That is an identity. Same thing as exponential identities. If I have some base raised to the m plus n, that's equal to that base raised to the m times that base raised to the n. These are all examples of identities. They're just equivalent math expressions. And that's what's happening in this objective, is you're trying to get better at identifying equivalent trigonometric identities or expressions so you can substitute in order to find limits. So I want to go back to really like the most basic trig identity, which a lot of your calculuses, I wouldn't say based off of, but it's one of the more fundamental ones that'll come up frequently. And if you memorize this one or understand where it comes from, it might make finding other identities a lot easier. You saw this in previous videos. We have a unit circle. I was going to make a joke that I drew it by hand, but it's really good, so I did not draw that by hand. Let me stop for 1 second. Okay, I got what I want to say here. So one of your most basic trig identities is called the Pythagorean identity, and it is sine squared. In this case, we'll say theta, just sine squared of some angle plus cosine squared of that same angle is equal to 1. Now, we actually could have written this like sine theta squared. that quantity squared. Usually with trig, the squared comes after the function, so really to avoid confusion that we're not squaring the theta, because that would be a different function altogether. So notice that I could have written it like this, like quantity sine theta squared plus quantity cosine theta squared equals 1. That would be the exact same thing, but usually with trig functions, you find the squared right after the function is said. Now, this identity comes from the most basic definition from the unit circle. Reminder that, oh, didn't mean to do that, so let's live put that back. There we go. So it comes from, again, it's a unit circle, which means that this hypotenuse right here is equal to 1. That is 1 unit because that's 1 radius from the center of the circle to the edge of the circle. So that's defined as 1. And with our basic trig definitions, if I wanted to find the cosine of this angle, well, the cosine would be equal to, the cosine of theta would be equal to the adjacent side, which we can just label x, like some value we don't know, all divided by 1, which if we just did that divided by 1, we're arguing that cosine of theta is equal to some x value. Similarly, if I wanted to define the sine of theta, well, that's equal just to, I'll call this some y value. So the opposite side divided by the hypotenuse, which we know the hypotenuse is 1. And so that really means we can simplify that equation to just be sine of theta is y. And that's why every single xy point on the unit circle, which is again just a way to organize the ratios of sides of right triangles, we can define it as an xy point, but we usually define it as a cosine of a given angle. We use the y value to be the sine of that given angle. So this identity, sine squared theta plus cosine squared theta equals 1, just comes from the Pythagorean theorem. That's why it's called the Pythagorean identity. We know that if I have a right triangle, which we know this is definitely a right triangle, that a squared one side plus b squared the other side is equal to the hypotenuse squared. So if I know the x value equals cosine, the y value equals sine, I flipped the order, but I could have sine squared theta plus cosine squared theta, or cosine squared theta plus sine squared theta equals 1. So that's where the Pythagorean identity comes from. That's really important to understand. Like, if we get where these come from and we start to recognize them, when we try these limits out, I think they'll feel a little bit less foreign, and you'll recognize that really are just substituting things that are equivalent expressions. So what I'm going to do now is sort of follow along with you in this video that I found. It's linked in the Google Classroom assignment. And as I play it, I am going to kind of watch it with you, and then I'll try to give a little more explanation where I feel like it could be beneficial for you all.
Today we're going to take a look at a magic hexagon. And this magic hexagon is going to help us in generating all of our trig identities. Okay, so this is the magic hexagon that we're going to use. We're going to place a 1 in the center of the hexagon, and then we will place the 6 trig functions around the outside of the hexagon as shown in the picture.
So it's a quick pause so I would definitely practice with me right now. I'm just going to, best I can, draw a magic hexagon. And it's magic in the same way the unit circle is magic. It's just a really clever way to organize information to make it easier to know our trig identities. So I'm going to draw, best I can, a hexagon. The 1 always goes in the middle. And then if you remember to start with tangent right here on this left corner, the rest sort of makes sense. We know that tangent we can define as sine over cosine, for the reason that tangent's defined as the opposite side divided by the adjacent. If I go back here, thinking about what would tangent of this angle be, well, tangent would be the opposite side divided by the adjacent side. The opposite side is sine, the adjacent side is cosine, hence tangent equals sine over cosine. So if you have that memorized, then the opposite of on the tangent side is just cotangent, and then it keeps going with whatever the opposite of these functions are. So the opposite of sine is cosecant, and the opposite of cosine is secant. And from there, I just kind of draw lines connecting through to make those little triangles, and now we have our magic hexagon. So back to the video.
For our quotient identities. All of our quotient identities can be found by either going clockwise or counterclockwise around the hexagon. In the example on the left,
So I'm going to explain this just really quickly, and I think I can stay here and just annotate on the screen, which would be kind of fun. So again, I just showed you how to define tangent equals sine over cosine, where it comes from the unit circle. If you're wondering, like, how can I, like, does it really work? Can I just go clockwise or counterclockwise? I'll give a counterclockwise example. So if you're wondering, like, how does sine equal tangent over secant? It usually goes to just things that cancel out. So if I was wondering, how does sine of theta, how is that equal to tangent of theta divided by secant of theta? Well, if we define tangent and secant, I guess give an identity or just substitute, I could rewrite this equation as sine of theta equals, we just saw a tangent can be defined as sine of theta over cosine of theta. And then secant theta, which we'll see in just a second, can be defined as 1 over cosine. And so now I have a much more complicated fraction, but I'm saying that sine of theta equals sine of theta divided by cosine of theta, and that whole quantity divided by 1 over cosine. If I multiply because now I have a bigger fraction, if I multiply the top and bottom of this fraction by cosine of theta, notice how this would cancel, leaving just 1 in the denominator, and then this would also cancel. And so now we're just left with sine of theta is equal to sine of theta. So it really just goes to substitution and seeing things that cancel out. But it's true if I go clockwise around the magic hexagon, I just go start with 1 and go to the next 2, tangent's going to equal sine divided by cosine. Sine will equal cosine divided by cotangent. I can also go clockwise or counterclockwise around it.
I'm demonstrating how we can generate tangent is equal to sine over cosine. All right, pick a spot along the product identities. I've got 2 different ways to find product identities. The example on the left here demonstrates that when we have a function that is between any 2 functions, it is going to be equal to those 2 functions being multiplied. So in other words, I've got sine and it is in between tangent and cosine. So that tells me that tangent times cosine is going to be equal to sine. And again, I can do this anywhere along the hexagon. All right, the second way that I can find a product identity is demonstrated over here on the right. When 2 functions are opposite of each other on this hexagon, then their product is equal to 1. And I've demonstrated that here. Tangent and cotangent are opposite each other on the hexagon. There's the 1 in the middle. So tangent times cotangent is going to be equal to 1.
I think she did a really good job explaining that. I just want to give one clarification, which kind of links to what I just said. If you're wondering how does tangent times cosine equals sine, it goes back to how we could define tangent as sine of theta divided by cosine of theta. And if I multiply that times cosine of theta, the cosines cancel. So I'm really just left with sine is equal to sine. And then right here, you're actually looking at the multiplicative identity of if I multiply a value by its reciprocal, it equals 1. Because tangent and cotangent are reciprocals, which I think you'll see in the next part. But I also could define tangent as sine of theta over cosine theta, and cotangent is defined as cosine theta divided by sine theta. You can see that if I multiply it through, I'd have sine times cosine divided by cosine times sine, or I could even cancel, but that whole value is just going to equal 1. I'll let her keep going.
So 2 different methods for finding the product identities. Okay, next we're going to take a look at our reciprocal identities. All of the reciprocal identities can be found by going through the 1. All right, so over here on the left, I've shown that sine is equal to 1 over cosecant. All right, and again, I can start anywhere along this hexagon that I want. Over here on the right, I am showing starting at secant. Secant is going to be equal to 1 over cosine. So all of the reciprocal identities can be found by going through the 1 that's in the center of the hexagon. Our cofunction identities. They can be found by going across the hexagon, either left to right or right to left. All right, and on the left, I have demonstrated going across here at the top. I've got sine is going to be equal to cosine of 90 minus our theta. And as all of them are demonstrated there, all three of those work that way. Going the other direction across, cosine and sine, that means cosine of theta would be equal to sine of 90 minus theta, going right to left.
I think she's doing a good job explaining. I want to give examples because this might seem like the weirdest one, like how is that true? But if we actually take a look at the unit circle, it makes a lot of sense, and it's true for all of these. If I start at sine, whatever the angle value is going to be equal to cosine of that same angle if you do 90 minus that angle value. So let me give an example using our unit circle. So if we go back to right here, let's imagine we're actually analyzing right here. I'll use degrees because she also used degrees. So right there, that is 60 degrees. So we're going to say that theta equals 60. Well, I'm actually going to use my hand trick. If we're trying to figure out our cosine and our sine values there, I would put down my index finger, and my cosine value would be 1, like radical 1 over 2. So my cosine value right there is just 1/2. This is at 60. And then my sine value would be, to use 1, 2, 3 fingers, which I would put under the radical. And radical 1 is just 1, so I left it as 1 over 2. So that's our cosine and our sine values at 60. That, I forgot the name of it, but I have it written down, I think, here. The cofunction. Those cofunction identities, we're arguing that cosine of theta is equal to sine of 90 minus theta. So we can see right now, like if theta is 60, yeah, sine and cosine are not equal at 60. But let's go back to, we're basically arguing that cosine at theta, which is 1/2, is going to be equal to sine at 30, because we're saying sine of 90 minus theta. So we're really wondering, is it true that sine at 30 is equal to 1/2? So now we're wondering about this point right here, because that's where it's 30 degrees. If I do my same hand trick for the unit circle, put down this ring finger for 30 degrees, the cosine value would be √3 over 2, and the sine value going up, this pinky, would go under the radical divided by 2. So it is just 1/2. So you can see, like, it's not random, it's just from this, this principle from the unit circle. If I have a certain angle, cosine and sine, if I take cosine at that theta angle, that's going to be equal to sine at 90 minus that same theta angle. And that's true for the other relationships, tangent, cotangent, secant, and cosecant. So
each one of the cofunction identities can be found by going across the hexagon, either left to right or right to left. The Pythagorean identities. Again, we've got a couple different ways that we can generate these. We can, on the left, we can either go clockwise or counterclockwise around the 3 inside triangles, starting at the top and using addition.
This is the one that I think I can do the best job explaining. So this really comes down to this right here. If we start with this identity we started this video with, all the rest of these, you can use the triangle strategy. If you start like at these points and you go clockwise around a triangle or counterclockwise, I think it's a little bit unnecessary. That's probably the hardest one for me to memorize. If you start with this, the way they derived, the way the rest of these identities are derived actually makes a lot of sense. So I'm going to start with that main Pythagorean identity of sine squared theta plus cosine squared theta equals 1. And the way that all the rest of those are derived is really just by manipulating this equation right here. So the first, like this is the original, so I'll put a 1 by it. Now to get to the next one, all we're actually going to do is, that's a terrible division sign, is we're going to divide by cosine squared theta. So if I were to divide the whole equation by cosine squared theta, well, I know that sine divided by cosine equals tangent, and it's also true that sine squared theta divided by cosine squared theta equals tangent squared theta, and that anything divided by itself just equals 1. So we'd have tangent squared theta plus 1. I know that 1 over cosine equals secant. It's also true that 1 over cosine squared theta is going to be secant squared theta. I'm going to pause real quick, just so you can see, back to the video. That was the first identity under sine squared plus cosine squared equals 1. It was tangent squared theta plus 1 equals secant squared theta. So I'm going to prove the rest of these really quickly, just so you can see where they come from. And then if you want to use the magic hexagon to find them in the future, you can do that. Or you can start with that basic Pythagorean identity and then just sort of manipulate the equation until you find the rest. So if I want to find another identity, what I could have done, instead of dividing by cosine squared theta, I could have started by dividing by tangent squared theta. Actually, I want to make sure I'm right before I keep going. Cool, good to know. I'm glad I checked it out. I was going to mess that up. So now if I have this equation, if I want to figure out another identity, this time I'm just going to divide by tangent squared theta. So if I divide this whole equation, again, if I divide the entire equation or multiply the entire equation by a value, I haven't changed the value of that equation. So now we're able to find another identity. Tangent divided by tangent is just going to equal 1. If I have 1 over tangent squared theta, that's going to be cotangent squared theta. And then if I have secant squared divided by tangent, I need to write that out just for my benefit. So that's going to be 1 over cosine squared theta divided by sine squared theta over cosine squared theta. So I have multiply both sides, and these are both squared, multiply both top and bottom. I'll just divide by that, so it's really multiplying by the reciprocal. So I'm going to end up multiplying this by, so I'm just taking this bottom and I'm multiplying by the reciprocal, because that's the same thing as dividing. Looks like these would cancel. So that's how they get 1 over sine squared theta, which is just secant squared theta. That's why this last identity, again, it's just changing how we define secant squared and tangent. So this is going to be equal to cosecant squared theta. And all this comes is just starting from this original equation and then manipulating. So now we can do a few more things. Instead of starting by dividing stuff, I'm going to start with the original equation and show how we can find a few more identities. Instead of dividing by anything, well, what if I had just solved this for sine squared theta? And to do that, all I would have had to have done is subtracted both sides by cosine squared theta. So another identity is sine squared theta is equal to 1 minus cosine squared theta. That's just solving the whole equation for sine squared theta. And now to find another identity, so this is actually the fourth one. So now to find another one, what I'm going to do is start to divide again. And if I divide this whole equation now by cosine squared theta, I know that sine squared theta divided by cosine squared theta is equal to tangent squared theta. And that's going to be equal to secant. 1 over cosine squared is secant squared theta. And then anything divided by itself is just 1. Notice how we also could have gotten here just by solving this whole equation for tangent squared theta. Then very last one, so that's the fifth one, and the sixth identity. We can divide this whole equation by sine squared theta, but what you'll see is that, make sure that's right. Yeah, I'm going to take a leap of faith. If I divide it all by sine squared theta, I'm going to end up with cotangent squared theta. So again, if I divided this whole equation by sine squared theta, I would end up with cotangent squared theta equals cosecant squared theta, and then all minus, all minus 1. I don't think that's right. I'm actually going to pause real quick to figure out what I'm doing. All right, so my bad. It was a quick catch up. If I had divided this instead originally by tangent squared theta, then I would have gotten this last identity of, this would have been 1 is equal to cosecant squared theta minus cotangent squared theta, which could have just been derived by subtracting cotangent squared theta from both sides. Stop share, last part of the video.
All right, so here's the inside triangles right there that I am talking about. So down here, I can at the top, sum of 1 squared equals, not making a difference whether you're going clockwise or counterclockwise. If you start at the bottom, you're going to use subtraction. So cosecant 3 inside, start at the top. All right, that pretty much.
So I'm going to pause there. That last bit, if you want to go back and watch that, is just her explaining how to use the magic hexagon. But all it is, and it's shown pretty clearly, if you start at sine, tangent, just how to create identities by going clockwise or counterclockwise within the little mini triangles of the magic hexagon, okay? As always, if you have questions, please let me know. I wanna make sure I hit all my key points. This is the main video for this objective, and I've linked all the other resources to be helpful. We need to know our trig identities in order to find limits of these upcoming calculus functions.